All right, everybody, I think I'll go ahead and get started. We've got people in person, people in Zoom. I'm recording this, so if you want to review any of it later, or if you have to leave early, or you just missed something, you'll be able to come back and pick that up through a YouTube video that I will send a link out to as soon as I compile that all. I'll try to get that done as quickly after the session tonight as possible. But this is our review session for the second midterm for Math 350, which is on Thursday, so 3 days from now. And what I would like to do, I have a lot of office hours throughout the week, of course, but I also want to just get you kind of tuned up a little bit, a little bit of practice to get ready for this test. And as I did with the review sessions for the first midterm, I'm mostly going to focus on problem solving. Looking at examples that would be maybe exam worthy. I'll try not to make them too hard. I'll try not to make them too easy. And somewhere kind of looking for the sweet spot of kind of what you should hopefully be able to do. And so, yeah, this will be just on top of the group works and the homeworks and the stuff that's in that resources folder. This will just be one more thing with another slew of problems for you to kind of look at. I definitely recommend that between now and Thursday, maybe somewhere around Tuesday or Wednesday, to give that sample midterm a try. The solutions are posted in there in that folder as well, so you'll be able to check those out. And if you got questions about it, or maybe you tried to solve it a different way, and then you want to know how that would work, if it would work or not, so that would be. That would be fine. Sorry, 1 second here. Let's get this thing. There we go. Yeah, and you can hang out as much or as little in my office hours as you need to. Make sure that you spend some of your study time on your own. It's easy enough to listen to me the whole week long and say, "Oh, I understand everything he said," and then you sort of get overconfident and you're like, "Oh, well, I must be ready if I understand everything." But it's also about being able to do the problems for yourself too. So make sure you spend a balance of time between that resources folder versus doing some of your own practice problems as well. As you know, the midterm is going to cover the last part of chapter 3, so that's 3.3 through 3.7. And then the first 3 sections of chapter 4. So we've only gone, in class, we've already moved beyond these sections, but at least for the exam, these are the sections to be focusing on. And I have not written the test yet, but you could imagine roughly a equal split between the 2 chapters. So chapter 3 is sort of about sequences. Chapter 4 is about functions, limits of functions, and continuity. So in some ways, there's similarities between them, but you definitely need to be able to keep those straight. And I have not written the test, as I said, but I may very well do what I did for the first midterm, which is give you the opportunity to take some things home. I'd probably give you roughly 24 hours to work on it, maybe 48 hours, something like that. If I do that, if I give you an optional take home, what will happen is I'll print out a blank exam, send it out to you guys, and you guys will, work on whatever parts you want. Try your best to really take home the stuff that you're going to maximize your points on. That didn't happen for everybody the first time around. So this could be, part of it is just the value of the problem. So I wouldn't take home a problem that's worth 3 points if there's another problem worth 8 points that I'm not sure how to do. But also, in addition to that, really try to make sure that you have your definitions down, your theorems down, that you can state those things. I just gave that quiz, right? And in that quiz you saw, I was trying to really make sure that you're, I'm not bluffing about this. I may ask you to put those terms in. You don't want to be taking home definitions and statements of theorems, right? You want to get your points for those during the exam so that then you can take home something where you actually have to solve a problem, where you have to create something or think about something maybe you haven't quite thought about before, right? Something like that would be more realistic for a take home. So anyway, just be mindful of that. I haven't decided for sure exactly how that's going to look, but there's a good chance that I'll let people take something home and turn it in a little bit later. Okay. Let's see. Yeah, so keep those flashcards coming, especially results that are famous and well named. So I'm not going to say on the exam state theorem 3.6. I won't do that, right? But I might say state Dr. Annan's huge remark about continuity of functions, or state the definition of a Cauchy sequence, or state the Bolzano-Weierstrass theorem for sets, right? What's the squeeze theorem? Things like that, right? So don't be surprised if I do that, and those are things that you can definitely make your flashcards for. Okay, in terms of the proofs of those results, well, I'm not going to ask during an exam for you to prove something that's very long-winded. And so some of these things, like the monotone subsequence theorem, for example, where you have to create this idea of what a peak is, and then you gotta, figure out, well, there's a couple of cases depending on how many peaks you have and stuff like that. It's hard to expect students to kind of pick, especially if they didn't know ahead of time to learn that, to expect people to do something like that. More likely, I'm going to ask you things that you practiced already once or twice. You saw it in the group work. Oh, and then it was in the homework. Oh, and then it was on the quiz, right? Stuff like that. So that's, I think, where I would try to focus my energy. And then also when you look at the sample test, you'll get kind of an idea of it. I don't like problems where you're either going to get it all right or you're going to have no idea, depending on whether you happen to study that or not. I don't like those kind of questions because it's not real. This is not a class about just sort of memorizing facts. It's about learning how to think about real analysis. And so I like problems that sort of assess people's ability to think in the moment on these problems. And so, things where you have a long-winded proof that's kind of complicated don't really serve that purpose very well. So if you have a question about it, let's say you studied a proof of some result in this section and you're wondering whether that's something that you really should be worrying about, you can ask me, during the week, and even if I haven't written the test, I'll probably have an idea about whether that would be reasonable. Okay. Does anybody have any questions about kind of just how this is gonna play out? Try to get to the exam a couple minutes early. Try not to have something you have to rush off to right at 2:50. So just in case you need a little extra time, I'm obviously going to try to make sure that it's all doable in the time frame. But just in case, it never hurts to. I mean, I don't think that Thursday is going to be a good day to do your oil change appointment like 45 minutes before the exam, right? I would try to keep your schedule cleared up a little bit so you can, be calm and focused going into the test. Okay, so with that as a background, I have about 16 problems. I took these off of the review from the last time I taught the class. I'm not going to do these all tonight. My goal is to maybe do about half of them tonight, and then I'm doing another review on Wednesday. And so for Wednesday's review, I'll probably do the ones that I don't do from here. I'm going to try, though, to cover all of these sections as best as I can, and just kind of see how this goes. And at least one of the problems I'm going to do is basically right off of the homework that you're working on for tomorrow night. So I'll more or less do one of those for you as well as we get going here. Okay, so let's just start off a little bit not too heavy. I'm going to start with something that I think we can do fairly quickly here, which is to give an example. Okay, and you should expect a question like this on my exam. I might ask you to give an example of something. Give an example of a function f that goes from the real numbers to the real numbers such that for all real numbers c, the limit as x approaches c of f of x does not exist, but the limit as x approaches c of the absolute value of f of x does exist. So in this example, we're supposed to just create a function, okay? And always be mindful of what the parameters are for this. It should be a function from R to R. So make sure that your function is defined for all real numbers. That's going to be important. But what we want is that the function doesn't have a limit anywhere, right? If you pick any C value, you cannot make this limit exist. But if you take the absolute value of the function, then it will exist. So just to remind you again, before we actually, you can be thinking about an example while I'm kind of recalling some things here. The limit of f of x as x approaches c equals L. What that means, just to kind of get it back on the board again, is, so the definition is, well, for all epsilon greater than 0, there exists a delta greater than 0, such that, and by the way, asking you for this definition might be like part A of the question. And then part B would be, give me the example. So something like that. If 0 is less than absolute x minus c is less than delta, then absolute f of x minus L is less than epsilon. Okay. So this might be a nice little problem here. Does anybody have any thoughts about how this function could be created?
Could it be a piecewise function?
A piecewise function. I kind of like that idea. And by the way, guys, there may be many correct answers here. So I don't want to give anybody the idea that there could only be one thing, but I like that suggestion that we kind of do it in pieces. Now, what kind of pieces do you want to make here?
Let's have 2 if x is even and -2 if x is odd.
Okay, x being even or odd, Danny, x being even or odd would imply that it's an integer. So just
okay.
remember here that x is going to be a real number. So instead of even and odd, would there be a different way to kind of parse up my real number line?
If x is a rational or irrational number?
I like that idea. I think that's a really good thought. So we can certainly do this, right? We can have two cases. And we can kind of define our function in these pieces. So we're going to define this thing here. Okay, so if we successfully define this function, then obviously every real number is in one of the two cases. So this will be a function from R to R. That should make sense. Does anybody? So Danny, you've done a good job setting us up. I'm going to see if somebody else maybe wants to give me an idea of how they might define the function. Keep in mind that you want to make sure that after you take the absolute value of it, that you get something where the limit does exist. And you want to make this easy on yourself. You want to make it so that this thing is, obviously going to have a limit, right? Does anybody have an idea how I might do my pieces here? -1 and 1. How about 1 and -1? Is that what you were thinking of, Danny?
Yeah.
Yeah, exactly. So I like that idea. 1 and -1. Okay. So, and by the way, it's not going to matter which piece you do -1 and which piece you do +1. So either way, but just as long as you create that difference, then you can see immediately that the absolute value of that is equal to 1 for all x's. And so in other words, it's a constant function. The absolute value of f of x is constant, and hence the limit as x approaches c of the absolute value of f of x is equal to the limit as x approaches c of just 1. And you can just state that that equals 1. Sometimes people will have a question like, well, how much can I assume and what do I need to prove? And if you had any doubt about something like that, of course, during the exam, you would come up and ask me, do I need to prove that the limit of 1 is equal to 1? And I probably would just say no, because in class, we did prove that the limit of any constant is just that constant. So you could cite that if you wanted to, or this is such a trivial fact that it really doesn't need an extra proof. Okay, so we've taken care of this part of it. The fact that the absolute value of the function does have a limit that exists. I need to convince myself that at any other value of c, the limit would not exist. So now let's fix a value of c, and I need to prove that the limit of the original f of x would not exist. Does anybody have a thought as to how we might be able to do that? I'm sorry? Density is definitely going to be a part of what's behind the scenes of making this work, but we can be really explicit. So am I going to use this definition to prove that the limit doesn't exist? Right, so we have multiple tools that we can think about. So I'm not sure if everybody heard this, but obviously we can always use the definition. The definition would be rather tedious. We would be saying, oh, suppose by way of contradiction that the limit does exist, right? So then that would mean that, okay, well then for all epsilons there exists a delta, and you'd have to pick an epsilon, a specific one. And you could make that work. Okay, but there is another way for disproving that limits exist, disproving that functions are continuous, for example. Then that is. Well, I'm actually thinking about something from chapter 3, back into the sequences section.
Oh,
I'm gonna find it for you.
Can I say that? Can I say the theorem? I think
Please.
I know it. If a sequence converges, then so does its subsequence to that limit. So if xn converges to x, then all the subsequences also converge to x.
That is true, but I don't think that's actually the result that we want to use here. Sorry, give me 1 second. I want to find the correct result. I think it's theorem 3.5. Yeah, I want to use theorem 3.5, which basically says that if you give me any fixed real number, I can create 2 sequences, one of them being a sequence of rational numbers that converges to x. The proof of that uses the density. Okay, so behind the scenes, the density of the rationals is there, but we can just state the theorem. So by theorem 3.5, right, we can create, and again, you don't need to know the theorem numbers for the exam. You can just say by a result from class that there exists, let's say, a sequence xn converging to C with xn in Q for all natural numbers n. So this is a sequence of rational numbers that converges to C. It actually doesn't matter whether C is rational or not. Okay, and so then what we can use is the result. I have to find it here. Sorry. No, it's going to be theorem. I forget whether it's they number the theorems and the propositions independently of each other, and that always throws me off. Yeah, it is a little bit hard to find the stuff when you're looking for it. 1 second. No. Let me just find this result that I'm looking for. I'm actually not using I don't want to necessarily use subsequences. I just want to use, it's a very simple result. Proposition 3.6. Sorry. You'll find it before I will, probably. Not the space theorem. Um. Oh, I am probably in the wrong section. Yeah, I'm looking for something in chapter 4. Right? Yeah, sorry, it's proposition 4.6, which which says that the limit of f of x as x approaches c is equal to L if and only if for all sequences that converge to C, right? That the limit of the image of that sequence is equal to L. Okay, so what we can say is if the limit as x approaches C of f of x, if that was equal to L, then the sequence f of xn would need to converge to f of C, which would therefore have to equal L. But what is f of xn? Xn is a bunch of rational numbers, they're all equal to 1, right? So this is just equal to, sorry, this doesn't, the f of C doesn't need to be there, I'm sorry, this is just to L. So if the limit of f of x as x approaches C equals L, that means that every sequence f of xn has to converge to L. And but this is equal to 1 for all n. And so that would imply that L equals 1. Don't have my contradiction yet. But what I'm going to do is I'm now going to use theorem 3.5 again, but with a sequence of irrational numbers. So I'm just going to say similarly, again by the same theorem 3.5, there exists a sequence y sub n converging to C with y sub n not rational for all natural numbers n. Okay, so then again, the image of that sequence would need to converge to L again, which would be 1. Because we've already said that L is equal to 1, but f of y sub n is always equal to -1. So the sequence is -1, -1, -1, -1, -1 forever, and that's supposedly converging to 1. So thus the sequence -1 converges to 1, and that's a contradiction. Because minus the constant sequence -1 actually converges to -1. So that would be it. Does everybody understand? The idea here is to create two sequences, one consisting of rational numbers and another consisting of irrational numbers. If this limit existed, okay, so this is kind of where your by way of contradiction starts, right? By way of contradiction, if this limit of f of x did equal some value, you can't say what value it is, so you have to leave it arbitrary and say it's maybe equal to L. Nothing that says it has to be 1 or -1, it could be something else, who knows, right? By way of contradiction, suppose that this limit does equal some fixed value L, and then based on that, you prove that L has to basically be two different things. It has to be equal to 1 according to the first sequence, but it has to be -1 according to the second sequence. Yeah, so I like this result because it does use some information about sequences from chapter 3 that we already studied. But then it also uses, this is by proposition 4.6, sorry, I'm honing my solution as I go along here. That was that proposition I was endlessly looking for. If this limit of f of x is equal to L, then if you make any sequence that's converging to C, the image of that sequence has to converge to L. When you're trying to disprove that a limit exists, a great way to do it, highly recommended, is by way of contradiction. And then use proposition 4.6. So focus on making sequences that converge towards whatever the limit point is. Here I've done 2 sequences. You often would need to do that. 2 sequences, both of which are converging to C, but whose images are converging to 2 different values. This is like the big picture view of how that kind of argument would work. So, does it seem okay? Seem reasonable? Obviously, if you just wrote down the function, I would give you partial credit for that. If you explained the first part, that the absolute value of f of x has a limit equal to 1, I would give you even more partial credit for that, right? So write down everything that you know. I mean, you might have a good feeling that this example is right, and maybe you're stumbling somewhere in the proof of the harder piece of this. But that doesn't mean to write off the whole problem, right? You definitely have got some of the right ideas there, and you should tell me as much of those ideas as you can, so I can give you as much partial credit as I can. That's always what I want to do. I always want to give out partial credit. Okay, let's try another one. Are there any questions here? Okay, let's try another one. This will be number 2. And this is going to be a true or false. Now, I don't like true false questions on my actual exams because it's mind games sometimes. People are thrown off by it. I never liked them. I'll just put it that way. I hated true false questions. So I probably won't ask it to you as a true false, but for a review session, I guess it's okay. So here's the statement. A bounded infinite subset of Q must have an accumulation point in Q. Now, where this is coming from is that you might remember the Bolzano-Weierstrass theorem for sets. The statement of that is that a bounded infinite subset of R must have an accumulation point in R. So the question here is, can I change R to Q? So can I make this still work? If I have a bounded infinite subset of Q, would I be able to assume that it has an accumulation point in Q? I see at least a number of people sort of nodding their heads no. I'm sorry? It's related to that. I wouldn't want you to just say that though. I would want you to actually create a counterexample. So at least, I'm not sure if everybody is 100% convinced yet, but I have several people kind of doubting this one. And if we think it might be false, the thing to do would be to try to create an example. So what we would be looking for is a bounded infinite. Now here's the thing. If we have a bounded infinite subset of Q, it's automatically also a bounded infinite subset of R. And the Bolzano-Weierstrass theorem for sets therefore guarantees that it will have an accumulation point in R, right? So the counterexample that we would want to be creating would be to try to make that accumulation point that the Bolzano-Weierstrass theorem gives us something irrational. Okay, so what's your favorite irrational number that you might want to have be your accumulation point?
Pi.
Pi, square root of 2. I know more decimal digits of pi. I'll pick pi. Okay, because we're going to actually use the decimal expansion of the number. But yeah, you can pick anything. It really doesn't matter. So what I'm going to do is I'm going to try to create a set whose only accumulation point is pi. Does anybody think? Oh, but it has to be a set of rational numbers. So I'll give you an idea. Would this be okay? Can I let S just be pi plus 1 over n? So now you got pi plus 1, pi plus a half, pi plus a third, pi plus a fourth. That's a sequence. And we did learn, did we not, that the accumulation points of 1 over n this was one of my examples for accumulation points, was that that's just 0. Right, and so what this looks like is it's just a translation, you're literally just adding pi to everything you had before, so that ought to just shift this thing over. I would agree that the accumulation points of pi plus 1 over n, I would agree that that is just pi. So would this be our counterexample? What's wrong with it?
Not a subset.
Right, these numbers here, pi plus 1 over n is irrational, right? You think about it, if pi plus 1 over n was rational, then you can subtract the 1 over n, which is also rational, and you'd end up proving that pi is rational. We know that's not true. So this does not work as our counterexample, although it's close, it's not too bad. So we need to kind of come back here and think again, how can we, I like this idea of a sequence that's converging to pi. But this sequence converging to pi is a sequence of irrational numbers. Is there a way to create a sequence of rational numbers that's converging to pi?
Off of each decimal point as you go.
Truncate the decimal expansion of pi, right, to some finite number of digits. Or you can use the same theorem again that we just talked about on the last problem. Just say, oh, well, by theorem 3.5, I can make a sequence of rational numbers that converges to pi. And the accumulation points of that sequence would just be pi. But I think it's kind of nice to actually list, give people a little more insight into how this works. So you could just say, all right, I'm gonna make the sequence of 3, 3.1, 3.14, 3.141, and so on and so on. I'm so proud of myself, guys. This year, I have learned a few more digits of pi. And so just to prove that, since I'm recording this and it's going on to my YouTube channel, I need to write down a few more. 141592, 3 point, just humor me for a moment. 3.1415926, 3.141, you guys can just go dot 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 if you want. 265. I am gonna get tired. 2658. 0.141592658. Oh, this is gonna take too long. 897. One more, just to prove it. 8979. Okay, and then I'm gonna say dot dot dot. Okay, so I'm doing pretty good with my, it only took me, all of my life until now to get what, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. At least I've got a dozen digits of pi there. Okay, great. So the accumulation points of S is just pi. That would literally just be pi. And so there's your counterexample. You have a bounded infinite subset. It's obviously bounded because all of the terms are between 3 and 4. It's infinite, clearly, because this is going to have an infinite decimal expansion. And pi itself is an accumulation point. If you take any neighborhood of pi, so we have to remember the definition of an accumulation point, every neighborhood of pi will contain infinitely many terms of this set S. Because if you just go far enough decimal digits down, even if your epsilon neighborhood is really, really small, even if epsilon is really, really small, eventually you'll have enough digits, decimal digits here, to capture all of the subsequent terms within that neighborhood. Okay, so this is kind of nice. That gives us a good counterexample, and I feel pretty good about that one. Okay,
I think you skipped 3 and 5 between the 5 and the 8.
did I write something wrong?
3.14159.
On this one?
5358979.
265.
35. Maybe not.
265. Is there a 3.5 there?
I think there is.
Oh gosh. Never mind.
Maybe
I
not.
might have it wrong. I thought I had it. You might be right. Well, in that case, I guess I can say I know. There's some digits I don't know, but then I know them again.
Yeah.
Whatever. Oh, man. Maybe this isn't gonna go on.
Scrap the tape.
I might have to edit this tape out. Alright, guys, let's do another problem here. Let me go to number 3. So we've done a couple things on sequences. Let's try this one. Let's try to prove that the limit as x approaches 3 of 1 over x squared is equal to 1 over 9. So this one is very specific. And you know, in some sense, you might say, well, math 350, I don't know why you put this on there, but making sure that you can do the epsilon delta definition on an example might not be a bad idea. In fact, I might even say that here. Prove this by using the definition. Because if I don't say that, then we have our limit theorems, right? And you can just say, oh, well, so the fast answer, I'll just say the fast solution would be, hey, the limit as x approaches 3 of 1 over x squared. So this is not the answer I would want. But, you know, technically you could give this answer if I didn't disallow it. You could just use the fact that limits respect quotients, products, sums, differences, and so on. The limit of a constant is just that constant. The limit of x as x approaches c is just c. And so there you go. There's your answer. So that's the fast solution, but it's not what I was looking for here, right? So I might have to be very specific with my instructions that I want you to use the definition. Let's just write down the definition. Again, so we have it here, so just recall that the limit of f of x as x approaches c is equal to L if and only if for all epsilon greater than 0, there exists a delta greater than 0 such that if 0 is less than absolute x minus c is less than delta, then absolute value of f of x minus L is less than epsilon. So I just want to have that on the board. We're going to be playing with that a little bit. And let me start my proof over here. Remember that on these kind of problems, the actual proof itself ends up being very short because you tend to go work out some scratch work on the side, and the scratch work is where the meat of the calculation comes into it. So the actual proof, I'll start right here, but make sure you save a little room to do your scratch work on the side. And what is the first sentence of my proof?
Epsilon.
Epsilon
Zero.
greater than 0. Be given, guys, rubber stamp it. I've said that so many times, I still sometimes see people kind of just loosey-goosey with this. So let's write that as a sentence verbatim. Okay, don't even try to modify it at all. And our job now is going to be to come up with the delta. And all of that is going to happen over here. So we're going to have some scratch. The scratch is ultimately, we're going to work backwards through this scratch. So we're going to kind of start from the conclusion that we want. So let's just go ahead and write that down. Absolute f of x minus L less than epsilon. That's the conclusion that we want. And we're going to be working backwards through this scratch. So the preceding step would just be absolute of 1 over x squared minus 1 over 9 less than epsilon. Okay? And be very careful to confirm for yourself, and just make sure you're comfortable with which direction these arrows go. A lot of them are going to be double arrows in these calculations, but once in a while there'll be a critical step where something only works in reverse. You need it to work in reverse more than anything, right? Having it work in the forward direction isn't so critical. And in fact, if somebody did this, if somebody only drew the backwards arrow here, I couldn't really say that this is wrong. It's perfectly fine. As long as I go backwards through the scratch work and get to this conclusion, I'm in good shape. But if it's a double arrow, I like to just reassure myself that that's a reversible step. Okay, what do you suppose I'm going to do here? Just simplify this fraction here, this difference of fractions, and that would give me a common denominator of what, 9x squared, I guess? And then in the numerator, I'll have 9 minus x squared less than epsilon, okay? Now, somewhere along the line, I like to orient myself to what I'm hoping to end up with here. Like, what's the end game of this scratch work? And I know that eventually I need to figure out my delta. My delta is tied in with how close x is to c. In this case, c is 3. So that means I'm looking at absolute x minus 3. So you always want to be looking at your scratch work saying, well, how can I get an x minus 3 to come out of this? How am I going to ever see that happen? And what you're going to probably notice here is that 9 minus x squared can be factored, right? So this becomes absolute of 3 minus x times 3 plus x. And it's still over. I'm going to take the 9x squared out of the absolute value bars because that's already positive anyway. So I can certainly do that. And okay, I didn't get x minus 3, but I got 3 minus x. So I can switch that around because absolute value bars don't matter. It doesn't matter which order I subtract things in. So I'm just going to go over to another column here. And I'm going to write that as absolute of x minus 3. And I'm going to move everything to the other side. Okay, so I still have my epsilon on the other side. I have my 9x squared going up there. And then I'm going to have an absolute value of 3 plus x. So far, everything I have done is totally reversible. These are double arrows forward and backward and forward and backward. Now, I would love to let this be my delta, except that I cannot let that be my delta because my delta cannot have x in it, right? So I need to come up ultimately with a delta that does not have an x in it. So do you remember what I need to do here to make sure that, or to find a way to kind of remove that x from this whole thing?
Initial delta value.
Yeah, we need kind of what I like to call a preliminary delta. So let me just go ahead and mention that here. A preliminary delta. And so I'll call it delta naught. And this just needs to be some sort of starting value that you're going to use to sort of control how big and how small x can be. So what would be a good preliminary delta value here?
1.
I would probably just use 1. Now, just to be careful with that. So here's where 3 is on my number line, right? And whatever my delta neighborhood is, I'm going to be allowed to consider x's that are within 3 plus or minus delta of that. So if I choose a preliminary delta of 1, then my x values will be ranging between 2 and 4. That's perfectly fine. What I really don't want on this problem is for 0 to somehow be inside of this neighborhood, because then you're like, oh, well, when I plug 0 in, right, I've got, denominators of 0 and stuff like that. Some of these steps are going to start to get questionable. So I would like to create an interval that does not include 0. This will certainly do it, right? Because if this is my preliminary delta, then x itself will be limited between 2 and 4. Okay, so I'm just going to kind of put a little circle around that. So that's where we are putting a range of values on our x. Now, here's the key step, right? This is probably for most people the hardest step. I am going to do a backwards only step here. I'm looking back to the scratch work. I had absolute x minus 3. I want to replace this with something. I'm going to put something here that is less than what's already on the right side. Smaller. Okay, we got to get that right. Not bigger, smaller. Why do I want to put something smaller here? Well, if x minus 3 is less than a smaller thing, then it will also then be less than a bigger thing. Okay, so I would like to take this fraction and I would like to make this thing smaller, either by making the numerator of this smaller or the denominator bigger. Okay, so what could I put into the numerator that would make it smaller and that would get rid of the x?
What do you mean get rid of it?
Well, I ultimately my delta should not have x in it.
Oh, like
So-
what value we're plugging in?
I need to put in, I wanna get rid of that x by having numbers plugged in. Now, I know that x is gonna ultimately be between 2 and 4.
Just scratch the square.
Well. If x squared is less than one, I guess x squared won't be less than 1, because we're going between 2 and 4 here. I was gonna say, that could be an issue as to whether x squared is making the numerator bigger or smaller as you go. It would depend on whether x squared was more than 1 or less than 1. It is certainly going to be more than 1 the way this is. So we could just scratch the x squared, I would agree with that. What-
Use 2.
What I did in my solutions is I put in 2 for x. You can do that or not do that, it will not make a difference. So I'm making my numerator smaller by putting in the smallest value, these are all the x's you're allowed to play with. The smallest x that you have would be on the lower end, which is 2. Okay. So this will make my fraction smaller. If I make the numerator smaller, then this numerator will be less than that numerator. Right? But I also need to pay attention to the denominator, so to make this whole fraction smaller, I actually wanna make the denominator bigger. So what am I gonna put in the denominator? I'm gonna put 4 in for x. So I know that feels weird to say, well, wait a minute, why are you putting x equals 2 on top and x equals 4 on the bottom? How can x be 2 things at once? Well, it can't, right? X is a fixed value between 2 and 4, but all you're trying to do is set up kind of a bound on what this expression could be. So there's no harm in, being selective and saying, well, in the numerator, I'm gonna put the x to be 2, and in the denominator, I'm gonna put it to be 4. And of course, this then comes out to 36 epsilon over 7. Okay, so that just simplifies very nicely as such. Okay, great, so is everybody okay with this? This is kind of the mucky step where you have to set up a preliminary delta that gives you a range of x values. This is kind of at the level that I hope people would be able to do. I mean, if you were taking like freshman level calculus, probably there wouldn't even be an x in the right side at all. But you can imagine, like, I could make this horrendous if I just made this function like 10 times messier. Then figuring out how to do all this would be, a much harder task. I'm not interested in seeing people's ability to stay calm with the most complicated possible function that there is. So this is kind of at the right level. I thought this might be a good one to show you guys. So what I'm gonna ultimately do now, guys, is I'm gonna come back to my proof and I'm gonna let delta be the mid of 1 and 36 epsilon over 7. And by the way, if we had taken John's idea, and if we had said, well, let's just drop the x squared completely, that would have been fine too. Then what we would have had here is 9 epsilon over 7.
Then I would have said add 6 to the bottom, then you'd have 9 over 9 and just use epsilon.
Oh, I see, instead of 3 plus 4, do
Yeah,
3
because right
plus
now
3
you got
plus
5 and 1.
Yeah, so you can certainly make this, a prettier delta over here. By cheating a little bit more on the numerator and the denominator, but just as a principle is something that will always work. I like doing it this way, by looking at what is my window of x values and how can I make the numerator smaller and the denominator bigger. And so that would be what I would do. Okay, great, so I've got my delta, so now what I do, guys, just get your rubber stamps back out. We're gonna take 0, we're gonna assume that 0 is less than absolute x minus 3 is less than delta. Okay, so that means immediately that x is between 2 and 4. We will know that because delta is at most 1. So x will be between 2 and 4, and so thus also, I'll just say also absolute x minus 3 is less than 36 epsilon over 7. And notice I didn't write 0 less than there. I could have, but I don't need to because I'm just gonna take this and just move right over to my scratch work now. And now go back and reverse my scratch work. So retracing the scratch. we get absolute of 1/x² minus 1/9 less than epsilon, and that finishes the proof. I think, we've done enough of these that it's hard to imagine an exam where you're not at least in one problem somewhere having to do scratch work, do an epsilon delta or an epsilon and not argument, something like that. Because we've certainly practiced it a lot. It's been in the homework, the group work, and now you're seeing another one now. So I think it's worth, and even in the lecture, we've had to do this kind of thing a few times. Question?
Whenever we do the preliminary data or the
Delta,
delta, we're always gonna use the min.
Over here in your proof, it will
Yeah.
always be a min. It will always be a min. That's absolutely true.
The times in class that we do, like our preliminary, it's like one, like C/2. That's because we don't necessarily know where the zero is gonna be. Okay.
Yeah, if this had been limit as x approaches c of
Yeah.
1/x² equals 1/c,
Uh-huh.
then I probably would have chosen my preliminary delta to be c/2.
Okay.
Or in fact, if I don't even know that c is positive, it might have to be the absolute value of c/2. Right, so yeah, that has come up on a couple of examples as well. So yeah, it's a good point. Okay, let's see. We can go on to another example. Okay, yeah, let's do this one. I'm on number 4 now. I like this one. So let's let xn be a bounded sequence. And then for all natural numbers n, we start with a bounded sequence and I'm about to make another sequence. So I'm going to define y sub n. Sorry, let's call it y sub n here. Define y sub n by definition to be the supremum of the set of x sub m where m is greater than or equal to n. And what I want to do is I would like to prove that the sequence y sub n converges. This is more of an abstract proof type problem. Get this other stuff out of the way for the moment.
What is in?
I'm sorry?
Is in?
Yeah, m is going to be, yeah, so, sorry, so m is in the natural numbers and m is greater than or equal to n. So, I guess I should mention on this exam, I won't ask you any question on this exam that I could have asked you on the first one. So I'm not gonna go off and start asking you a whole bunch of questions about supremums and infimums that are just, going back to chapter 2. But that's not to say that you might not see a supremum or an infimum somewhere. In fact, even on the homework you're working on for tonight, there's an extra problem that has an infimum in there. So just keep that in mind. I wouldn't spend a lot of time studying the stuff for the first midterm right now, but it shouldn't be completely like erased from your mind completely, because it could come up. This would be an example where that might come up. So I always like to pause and think about this for a minute. One thing I would like to point out is that they're not asking us to say what the sequence converges to. Now, that is important because that pretty much tells me if I'm not asking you what it converges to, it might be because we don't know what it's going to converge to. And I can't ask you what it converges to because we don't know. If we don't know what something converges to, by the way, then I can't really use the definition. Because the definition is, for all epsilon greater than 0, there exists an n naught in the natural numbers such that if n is greater than or equal to n naught, then absolute of y yn minus y is less than epsilon. So this definition of the convergence of a sequence requires us to know what the limit of the sequence is. And we don't know what it is, and we're not even being asked to show what it is. It'd be different if it said, prove that it converges and then find the limit, right? Which is kind of like that quiz problem. But this doesn't even ask you for that, and if it's not asking you for that, it seems unlikely that you would be going all the way back to this definition. So that's my first comment, is that this problem is probably not going to be done using the definition. So I want you to be thinking about how else can we prove that sequences converge besides the definition? Could we show that it's monotone? And what else would you want to show?
It's bounded.
That it's bounded. Exactly. We have this other tool called the monotone convergence theorem. If the sequence is bounded and monotone, then it converges. But it doesn't, we don't know what it converges to, right? Let's just, before I love that idea, actually. Let's see, that's exactly right. Before I actually go into that, I just want to maybe give us a reason to think that maybe this is going to be monotone. If I look at just what is y1, right? So this is just scratch for now. I'm not even doing a proof yet. I just want to kind of get the idea behind what's going on. So y1 would be what? The supremum of all of the x's starting with x1. So it would be x1 and then x2 and then x3. It's the supremum of that set. So remember, supremum is least upper bound. Okay, and what is y2? Y2 would be the supremum of, so now n is 2. So it'd be the set of all the x's starting with x2. So that would be x2, x3, x4, and so on and so on, right? And one more, y3, that would be just the supremum of starting with x3, x4, x5, and da 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 da. Right? Guys, the sets are getting smaller. They're kind of nested together. One thing is a superset of the next one, which is a superset of the next one, and so on. I want you to think about the supremum, the upper bound. Right? Anything that's an upper bound of the first set is actually an upper bound for all of them. But it's actually possible, since as we go down the line here, the sets get smaller, it might be possible to create an upper bound that's smaller here than the one that we have here. Do you agree with this? Just as a little note, this one does rely a little bit on knowing and remembering some stuff about supremums. But if you had two things that were subsets of each other, I'm pretty sure we did a homework problem about this in chapter 2. If one set was inside of another set, then what we could say, so if here's B, then inside of that we have A, and we're looking for the supremums, right? The supremum of B is way over here, but the supremum of A is just right there, right? So what we would expect here is that the supremum of A would be less than or equal to the supremum of B. And in fact, this was a homework problem that you did about a month ago. It's been a little while. So we have that relationship here. We have a set that contains the one below it, which contains the one below it, and so on. So this supremum is greater than or equal to this supremum, just greater than or equal to this supremum, and so on. So what I think we could then say is, so because Lindsay's idea is let's prove it's monotone, and my thought is, well, is it monotone increasing or is it monotone decreasing? Because we want to prove it, that would be the most reasonable thing to do. And what I think I would probably do, and now I think I'm ready to come over and start the actual solution. This was all just scratch work over here. What I think I would probably start off with, guys, is just a note that well, actually, if I just create a set, let's call it S sub n, and that's just the set of the x of m's where m is greater than or equal to n. So I'm creating a set here, guys. You wouldn't necessarily have to do this. So then S1 contains S2, contains S3, and so on. So that's just really reflected by what's in the scratch over here. First set, S1, contains the second set, which is this one, S2, which contains S3, which is this one. And so therefore, by this note, the supremum of S1 is greater than or equal to the supremum of S2 is greater than or equal to the supremum of S3 and so on, right? But what are those supremums? Those are just these y's, right? So in other words, that is y1 is greater than or equal to y2 is greater than or equal to y3, and so on and so on. So y sub n is, as Lindsay suggested, she's right, this is monotone, and specifically it is monotone decreasing. It is monotone decreasing. Yeah.
Does this count as a nested interval?
It's kind of, yeah, these would be considered nested intervals. I know there's a section in the book about nested intervals. I didn't cover it.
Okay, I was like,
You
I
don't need to
remember
know a
this.
whole bunch of theory about nested intervals. This is just one set inside of another, inside of another, inside of another, and you can just take that at face value. You don't need to know anything special beyond that. Okay, so is everybody good with this? We are halfway to being able to use the monotone convergence theorem. It has to be monotone, which we've already approved, and then the next thing is going to be to convince ourselves that it's bounded. Now, as soon as the nice thing about proving that it's monotone first is you get your upper bound immediately, which is always just the first term. So then I'm just going to make that as a note that y sub n is bounded above by y sub 1. Okay, so we certainly know that. And the question is sort of how low could this thing go? And there is something over here we haven't really used yet. I mean, there's part of this assumption. What have I not really been talking about so far?
That makes sense, Becky.
Right, so starting at the very beginning, the original x's, now that's not what we're looking at now, but the original x's are bounded. Okay, so that means that this entire set is bounded. In fact, so is this one, so is this one, and so is this one, right? And what does that tell me? So these sets are bounded. And not only that, as you go along, the bounds are getting, narrower, if anything, because your sets are getting smaller as you go along. So these y sub n's, which are supremums of some subset of all of the x's, so it's a supremum of a bounded set. So if this was not bounded, okay, can I just do this for a second? If the y sub n's were not bounded below, that would mean that these y sub n's go off towards negative infinity, right? Well, then that means that your supremums of these x's get huge negative. And that's going to violate the fact that the xn is a bounded sequence. So what I guess we could say here, guys, is that since xn is bounded, I would like to bring that into the proof now. Since that is bounded, then can I just say, let's try and formalize this a little bit. There exists a b greater than 0 such that the absolute value of xn is less than capital B for all natural numbers. This is more or less the definition of a bounded sequence. So all of these numbers are between plus and minus b. So your supremum of your set, if I have a bunch of numbers that are all in here, right? then do you agree that the supremum of any subset of this would have to be less than or equal to b? So in other words, every one of these y sub n's is less than or equal to b and also greater than or equal to negative b. Right? I mean, the supremum could be negative b. If this is the only point I have, right? Then my supremum would be negative b. But the point is that the supremum of Sn is greater than or equal to negative b for all n. That is y sub n is greater than or equal to negative b for all n. Yeah. And that means it's bounded below. It's already bounded above, and it's also going to be bounded below by the same bound that the xn sequence is bounded by. So. Okay, so it's bounded above, it's bounded below, so y sub n is also bounded. And I mean, if all the x's are between plus and minus b, then your supremum of any subset of them, right, can't be less than negative b. It's got to be at least negative b. So it's got a lower bound, and that would be for all of these y sub n's. So it's bounded and it's monotone. So by the monotone convergence theorem, y sub n converges. Y sub n converges. I don't like that problem. It's a nice one. Okay. That feel okay to everybody? All right. Super. And erase some of this again. Yeah, it's a little tricky. I'm not sure I'd put this on an exam because it's just a lot of notation and stuff, but I still think it's really good for practice purposes. Okay, everybody good so far? We need to take a break or keep going? Good? Are you happy? Or are you still thinking about that?
We'll come back.
Come back to that. Okay, we'll come back to that. Let's do another one. Let's go on to number 5 for now. I'm gonna hit you with another true false. Again, I probably wouldn't do this on the actual exam, but I like this little question, so we'll do it as a true false. We're gonna let f and g be functions from R to R. And then the statement is if the limit as x approaches c of f of x times g of x exists, then is it true that the limit of f of, so this is f of x times g of x here, then is it true that the value of that limit, is it true that the value of that limit is just the product of the limits of the individual functions? So limit as x approaches c of f of x times the limit as x approaches c of g of x. So this is the statement. Much more, this would be a very reasonable test question, but I probably would tell you whether it's true or not, and then ask you to take it from there. This statement here looks familiar, maybe. It actually looks just like our limit theorems for functions. So maybe this has something to do with that. We have to remember what that theorem says. What that theorem says is that if this, if this limit exists, right, and this limit exists, then this limit will exist and it will be the product of the individual limits. So is that all that this statement is trying to state, or is it a little deeper than that?
We don't know that the limit of f of x and g of x already exists.
It's a tricky question because on the right hand side, we're looking at the limits of the individual functions and nothing in our assumptions says that those exist. So I'm already pretty skeptical, again. I'm pretty skeptical about this one. If it had said, limit of f of x exists and limit of g of x exists, then the limit of f of x times g of x equals this times this, you would say, absolutely, by the limit theorems, right? And you wouldn't even be having to prove anything more than that. You would just state it by the limit theorems. By the way, the proof of this, we did it in class. It was messy. It was pretty tricky, if you might remember. I would not probably go that complicated on you. Maybe something with addition. So the same thing could be, I could do the same game with f of x plus g of x. If the limit of f of x plus g of x exists, then does that mean that the limit is this one plus this one? And you again have the problem that if you don't know that the individual limits exist, then you can't really make that work. So that would have also been false, even if it had been with plus signs. But anyway, so what I'm gonna suggest here is that this is false. Now on the exam, I probably would tell you that, and I probably would say, give me a counterexample. So what I'm gonna have us try and do is make two functions, right? I need to make two functions, and I want to do it in a way that it'll be as obvious as possible that f times g has a limit. And hopefully as obvious as possible that f itself and g itself individually, or at least one of them, doesn't have a limit. Doesn't have to be both necessarily, but at least one of them hopefully doesn't have a limit. So I'm wondering if anybody has an idea how to maybe do this.
We can do what we did earlier with rational and irrational, but like 1 and -1 and then -1 and 1.
So we do like 1 and -1 for x in Q, and this for x not in Q. So this has a limit nowhere, right? And then g of x, you would do same thing.
Opposite -1.
Oh, -1 and 1 with the same conditions here. So these two limits individually do not exist. So by the earlier problem. See how I snuck 3 or 4 other problems in between? Just to see if does anybody remember the one we did 45 minutes ago? Yeah, so by the earlier problem, the limit of f of x, I haven't even chosen a c value, it's not gonna matter, right? And the limit of g of x as x approaches c do not exist, which means that the right hand side here, it doesn't make sense. And then if you look at f times g, I'll just say, however, the limit as x approaches c of f of x times g of x, now we can literally say that this is just the limit of 1. Because f times g is 1. Negative, sorry, -1. And so that's just equal to -1. Yeah, that would do it.
We use x, f of x equals x and g of x is 1 over x, just to make it a lot less writing.
I was gonna actually so this one I took from my old review session from 4 years ago, and I watched what I did, and I absolutely did that. So there is one little issue with that though. So the issue is, so this limit individually would exist. See here, both of these fail to exist. And you don't need them both to fail. You only need one of them to fail for this right hand side to be nonsense, right? So this one would exist, right? The limit of x as x approaches c would be equal to c. But then what you're saying is you want to do 1 over x, but there's one little problem with that. Which is you can't plug in 0, but g is supposed to be definable on all real numbers. So what you have to do, you can make that work. What you have to do is you have to say if x is not 0, I'm going to use 1 over x. And then because you want the product of these to come out to be 1, you can just put 1 here if x equals 0. And then that should do it. Actually, So what is the graph of this? So the graph of this thing, here's 1. Coming along like that, right? So if I don't think about 0 yet, and I just look at, so I'm graphing f times g. What is f times g? So as long as x does not equal 0, it's just x times 1 over x, which is 1. So when x equals 0, I'm asking what is f times g, it actually would be here. Right? But that doesn't matter because, you know, the point is that even if c is 0, the limit of f times g would be equal to 1. Right? Remember, limits don't care what's happening right at that value. So the limit as x approaches 0 for this graph would be 1. And that would be fine, but the limit of g of x itself. So what is g of x? G of x is a graph that looks like this, right? 1 over x. And we're choosing to put g of 0 equal to 1 like that. Again, you could put it here, you put it anywhere you want. But this limit does not exist as x approaches 0. So I specifically would want to use c equals 0 for my counterexample. Because if I don't choose c equal to 0, then both of these limits do exist individually. And so we don't have a counterexample. We need a counterexample, so I would choose c to be 0, and I would say, look, if I take f times g, there's my graph, and the limit as x approaches 0 is 1. Okay, so the left-hand side is equal to 1. But if I break it down with the right-hand side, I've got the limit of f of x being 0, and the limit of g of x being dne. So you got 1 equal to 0 times dne, and that's your contradiction, or that's your counterexample. That make a little bit of sense? Let's see, are you okay?
Yeah, I'm just having a little trouble
With
understanding.
this one?
Yeah, right at the bottom where we did f x times g of x is equal to the limit of -1. How do we get it?
So if you take f times, so if you pick any x value whatsoever, right? And you plug it into f, you're either gonna get 1 or -1. If you plug it into g, you're either gonna get -1 or 1. Whichever sign you get for f,
Oh,
the sign for g will be the opposite.
Okay.
So if you plugged in a rational number, you have 1 here and -1 here, and that'd be -1 for a product. But if you picked an irrational number, you'd have -1 here, but you'd have 1 here. And again, the product would be -1. So yeah, good point. So I like both of these examples actually. You know, as so we've actually given 2 things that might work. And I like problems where there's multiple ways to kind of give a counterexample. That's a nice problem. Okay, great. Well, let's move on and do some more stuff. Back over here again. Done 5 problems. My goal is to get at least 8 done tonight. So I got half of them done anyway. Let's do this one. So this is number 6. I would like to prove. Well, sorry, I would like to compute. Sorry. Compute. And then with proof. So I don't just want to know what the answer is here. I want it to be proven as well. I would like to compute with proof the limit as x goes to infinity of 2x squared minus 5x plus 6, all divided by x squared plus x plus 1. Okay. We do need to notice that this is limits involving infinity. So for the first time tonight, I'm doing an example where x is not approaching c, it's approaching infinity. So I might, before I actually do the problem, I'm just going to recall the definition of that for you. Recall that the limit as x approaches infinity of f of x equals L means. So here's the definition, for all epsilon greater than 0. So normally there was going to exist a delta, but in this case, if you remember from this is the one you took the video notes on, it's a little 20-minute video I made. There exists an alpha greater than 0 such that if x is greater than alpha, then absolute f of x minus L is less than epsilon. Okay. And again, in my video, I suggested that you try to write down what would it mean for the limit of f of x equal L as x goes to minus infinity. Or what would it mean for the limit of f of x as x approaches c to be plus infinity or minus infinity. So that's something worth doing. And take that as an exercise for yourself to write down all those little variations of this. Okay. This is another thing I love to do, is I love to show you the plus infinity example and then ask you to do the minus infinity example or vice versa. It's a very typical thing. I just tweak it a little bit and ask you to work through it. So this is the idea. Now, in order to use this definition, I have to sort of know what L is going to be. Does anybody think they might know what the L value is for this problem so that we can get it correct to begin with? 2, right? Basically, the way you think about this is you look at the numerator and denominator. If they are both polynomials, you compare the degree. And in this case, they're both quadratics. So you just look at the ratio of the leading coefficients. They probably go over this a little bit in your calculus class. So the claim is that that's equal to 2. So that should be the answer. If this was a 10-point problem, I might only give you 1 point for writing that down. Okay. Sorry, guys, I'm doing a study session.
Sorry.
That's okay. So I might claim that that's equal to 2, and I might get 1 point out of 10 for just writing that down. But we really want to do better than that. So the way we are going to do this is we're going to start off with what sentence? Thank you. Let epsilon greater than 0 be given, period. Exactly like that. And our job now is to come up with the alpha value. And for that, I need some scratch. And we're going to kind of work backwards again, starting from absolute f of x minus L less than epsilon. And the first step is just put in everything that we are looking at here. So the f of x is just 2x squared minus 5x plus 6, all divided by x squared plus x plus 1. And from that, I need to subtract my 2, which is what I claim that the limit is, and we're going to have that hopefully end up being less than epsilon. So this is going to be similar to one of the ones we did earlier tonight, but a little bit different because we're searching for an alpha here that's greater than 0. So my first step here is going to be what, do you suppose? Combine it together into a common denominator. I like it. Okay, so the common denominator is just going to be x squared plus x plus 1. And in the numerator, I have 2x squared minus 5x plus 6, but then I have to subtract 2 times the quantity x squared plus x plus 1. And I still want the absolute value of all of that to be less than epsilon. And I know I'm going a little fast, it's just to save some time during the study session. Most of this is not too hard to believe. Let me clean up this numerator just a little bit, kind of simplify that. I'll do one more fairly easy step. If I take negative 5x, I'm going to subtract 2 more x's. That looks like negative 7x. And then I have a plus 6, but then a minus 2, so that should be plus 4. All divided by x squared plus x plus 1. And this is still less than epsilon. So far, it's just algebra. It's just algebra. Okay. And unlike the traditional limit definition where you're kind of trying to figure out, well, where's absolute x minus c? Remember, we did this earlier, we took this thing and said, well, where's absolute, can we factor it, can we like manipulate it to get the x minus c to show up? Well, in this case, we don't even have a c. So I don't really know what to do with that. Well, I'm just looking for an alpha such that if x is bigger than alpha, something happens. Right? So it's maybe something we haven't practiced quite as many times, but it's still a nice thing to kind of think about. You know, one thing that's kind of annoying is the absolute value bars. We could get those to go away because if I choose a preliminary alpha that's, let's say, greater than 0 already. If I say I'm for sure gonna, well, in fact, we are required to find an alpha that's greater than 0. And if x is greater than alpha, which is greater than 0, then this denominator is for sure gonna be positive. Positive number plus a positive number plus a positive number, it's gonna be positive. We're gonna be able to get rid of the absolute value bars there, right? Now, the numerator is actually 0 right at 4/7, I believe. Okay, and if you go larger than 4/7, what happens is the numerator actually becomes negative. Okay, but let's take that 4/7 is bigger than 0, so I'm gonna do that, I'm gonna assume that alpha naught is greater than, actually, yeah, let's just say equals 4/7. If we only allow x's that are larger than that, then the numerator will for sure be negative, the denominator will for sure be positive. And so we'll be able to get rid of the absolute value bars accordingly. So I'm gonna just do a backwards arrow here. This is based on this little preliminary. This is a preliminary alpha. Because the numerator for x's that are bigger than 4/7, the numerator is actually negative. So when I want to remove that from absolute value bars, I actually just switch the order of it. So it's actually going to turn into, what is it going to be? 7x minus 4, but without absolute value bars. Over, and then the denominator, as we already have said, will also be positive. So we get rid of those absolute value bars by making that preliminary alpha naught. So if x is greater than 4/7, right? Then the numerator will be positive, the denominator will be positive, and so these absolute value bars actually are unnecessary. So if this is true, let's always make sure we can go backwards. If this was true, then would this still be true? The answer is, if x is bigger than 4/7, then if this is true, the denominator doesn't change here, and the numerator, just because it's being put into absolute value bars, this replacement is totally legitimate as well. Yeah, okay. So now, again, practicing one more time on this. I want to set this up so that if this is true down here, then this will be true up here. So that would mean that I would like to put something here that is bigger than that. So I want something bigger. I just want to make sure, does everybody understand that? I want something, I'm going to make a fraction here that's larger than what I see right here. Because if the larger thing is less than epsilon, then something smaller than it would still be less than epsilon. So the question is, how do I make this fraction larger? I can do it in two ways. I can either make the numerator bigger or I can make the denominator smaller. Can somebody tell me how to make this numerator bigger in a way that will simplify what I have?
You can take out the -4.
I can take out the -4, exactly, I can just go 7x. Alright, so I get rid of that, makes the numerator bigger. And then is there a nice way to make the denominator smaller? Get rid of the +1. get rid of the +1. Now, if I only get rid of the +1. You know, you can also get rid of the x too, because the x is gonna be positive. If you only got rid of the +1, that would actually be okay, and then you could factor this and cancel the x there, and you'd eventually be able to solve for x. But I think it'll just be even easier if we just kind of go all the way to that point. Okay, so I've made the denominator smaller, I've made the numerator bigger, so if this is true, then surely this is true. You with me? Okay, now this one is a double arrow, I just cancel the x and I get 7 over x less than epsilon. And now I do one more double arrow where I just flip the epsilon to the other side and I move the x to the other side. So x is greater than 7 over epsilon, and that is going to be my alpha value that I combine with the preliminary one that I had over here. Okay, so let's go back now to our proof. Is everybody with me on this? The scratch work is really the hardest part of it. But I also want to reiterate that if you get tangled up in the scratch work a little bit, but you have the big picture of it and you get it set up right, you know what the right answer is, and you show me that you can play with this definition, and maybe you get tangled up because you're just anxiety on the test or something and you get stuck somewhere. Try not to let that like totally ruin the problem, because you're gonna get almost all the credit for it if you're just missing one little piece here. Like everybody always focuses on the one step, like this is the key step or whatever, but that's not the only step, right? So just in terms of strategy for your tests, you know, if you are doing a lot of good steps along the way, I can give you credit for everything you've got there. So just keep it going as best as you can. And now what I'm gonna do is I'm going to choose alpha to be the, well, what am I gonna choose it to be? Is it min or is it max? Here's my number line for my x's. We took a preliminary delta of 4, 7. So we said, okay, we're only gonna look at x's that are over here. And then we picked another alpha, which is 7 over epsilon. Let's just say that's right here. I don't know where it is exactly, which means we're only gonna look at x's that are over here. So what should it be? It should be a max. It should be a max. Now that's a little weird, because maxes were mostly showing up when we were doing the and nots back in the sequences stuff. But because of the nature of this definition, right, we actually need to, you always want to pick the thing that will restrict the x's the most. And in this case, x is going off to plus infinity. So what restricts it is just the left-hand endpoint of that ray of x values. So you want to make that ray of x values as small as possible. So I'm going to choose the max of 4/7, comma 7 over epsilon. And obviously that is greater than 0. Add that there. Both of those numbers are greater than 0. And then it's just a matter of checking it. So let's assume, now we just get into it. We do the actual verification. Assume that x is greater than alpha. So x is greater than 7 over epsilon. And if x is greater than 7 over epsilon, then we come back over here and we retrace through the scratch work. There is this one step that requires x to be greater than 4/7 as well in the middle of this backwards tracing, but we don't even really need to say much about that. So retrace scratch to get absolute value of f of x minus 2 less than epsilon. And that would do it. All right. That seem reasonable? Okay, perfect. Okay, let's do.
Oh, I do have one question.
Please.
So for like an exam on a test, like for the double arrows, what if we have like we put like a double arrow for a part where it's only back arrow?
I won't like that 100%, but I might make. a point off on that. I don't know. It'd depend on how much of the big picture of the problem it was. It would not destroy your problem at all, but I would be a little bothered that because some of these steps are not reversible, and it is important that we get them going in the correct direction. So I might flag that in a minor way. So do your best to get that part right if you can. Does that answer your question?
Yeah, it does.
Okay, great. Okay, so let me see. Oh, I already did this one too. So I've done 1, 2, 3, 4, 5. I've done 6, right? Okay, great. Let's do another one. One of the ones I definitely want to do tonight is one that is basically from your homework that's due tomorrow night. So I want to do it, and I know a couple of you have already done this because you've asked me about it, but I hope you won't mind. It's a really nice problem, and I think it'd be good to help everybody with it. So this is going to be number 7, and this is very similar to one of the extra problems in the homework assignment for tomorrow. So I'm going to do the following, guys. I'm going to suppose that f is a function from a closed interval AB to R, and I'm going to suppose that it is increasing, by which I just mean, we're going to talk much more about increasing functions when we get after spring break, but it just means that if x is less than y, then f of x is less than or equal to f of y. And what I want to do here is do a quick little proof, and I'd like to prove that f is continuous at B. So the one in the homework is continuous at A. So I'm going to turn this problem around and do the other side of it. If and only if f of B is equal to the supremum of the set of the f of x's, such that x is an element of the half open interval from A to B. So the one that's in your homework for tomorrow night is looking at f being continuous at A, and it's describing it in terms of f of A being equal to the infimum of f of x on that interval. So this is just turning it around, and I'm only turning it around because I want to, well, first of all, some of you have already done the homework, so I'd like to give you something new to look at, but also this way I can, without doing your homework for you, I can more or less give you a great model, and then it'll still be some work for you to figure out how it goes from there. This is a 2-direction proof, so we have to go both directions. So I'm going to start with the forward direction, and I'm going to assume that f is continuous at B. And I won't write it all out again, but remember what that means. That just means for all epsilon, there exists a delta such that blah, blah, blah. We're assuming that, which means that we will ultimately be able to pick any epsilon that we want, a specific one. So we want to be on the lookout as we're writing this out. We want to be on the lookout for like, what would be a good choice for the epsilon that we want to play with. And so that'll maybe come to light as we get a little further into it here. By the way, I might draw a picture on the side over here. I don't mind pictures at all. I mean, they can give you some intuition sometimes, and it's not going to be a proof, but it certainly is, you know, it's not the worst thing in the world to have a picture here. We're just saying that if we have an increasing function going from A to B, so it's going uphill, right, something like that. All that we're really saying is that if you take the range of the function, all of the output values, right, you can kind of see where they are. They start at f of A, sorry, and they end up here at f of B, right? That this f of B is the supremum of all of these values, which are all the outputs of that function. It kind of seems reasonable. Okay, so far so good? Now, we have to prove that f of b is a supremum. The supremum means least upper bound. And you might remember from the first part of the course that if you want to prove that a number is a least upper bound for a set, there's two parts to that. You have to first prove that it is an upper bound for the set. And then you have to imagine some other upper bound, which I usually call gamma, and prove that gamma couldn't be, couldn't be the least up, couldn't be in this case less than f of b. Okay, so let's do those two parts. Now, one thing I can tell you is that since f is increasing, right, it's an increasing function from left to right, then would you agree that f of x is in fact less than or equal to f of b for all x in the domain? So the right-hand endpoint has got to be the biggest value. If you compare that with any other x value, the f of x values to the left of f of b have to be lower, right? Well, that already proves that f of b is an upper bound for our set. Okay. So f of b is an upper bound. Keep in mind, in your homework, you're going to be writing lower bound, and everything's going to get flipped over. But f of b is an upper bound for the set of f of x's, such that x is in the interval from a to b. And I should point out that we aren't even using the assumption yet. The assumption was that f is continuous at b, but to get this part of it, to just get that f of b is an upper bound, we don't even need to use the fact that f is continuous at b. So far we haven't even touched the assumption. We're going to need that for the second part. So next, I'm going to assume that gamma is an upper bound for this set of f of x's. This is such that x is in the interval from a to b. Assume that we have some other upper bound for that set, and the claim will be, the claim here is going to be, by the way, guys, stop me with questions if anything's unclear here. It's a good chance I'm going to choose to grade this one, because I really like this problem. Or I should say the homework version of this problem, which is just very similar, basically. So the claim is going to be that f of b is the least upper bound. So that would mean that f of b should be less than or equal to gamma. So if we had some other upper bound for the set, f of b should be less than or equal to it. Well, I am going to approach this by way of contradiction. This is the trick. This is the trick. So by way of contradiction, suppose that f of b is strictly greater than gamma. So in my picture then, my gamma is going to be maybe right here somewhere. So f of b is here, and it's greater than gamma. It's greater than gamma. Okay. Now, I mentioned that we have not used the fact that f is continuous at b yet. And we're obviously assuming we will use that. So that would mean that, again, for all epsilon greater than 0, there should exist a delta. But I said at the start of this proof that we need to be on the lookout for what would be a choice of epsilon to use that would be something that would have to be greater than 0. I mean, it's got to sort of stick out at us as something that would be positive. It would be a positive value, but it would be some fixed value. Did anybody see it yet?
F of b minus
Gamma. F of b minus gamma, right, would be greater than 0. And so that would qualify as an epsilon. Now, I don't know if it's going to work yet because I haven't thought this whole proof through, but it seems reasonable to consider or to let epsilon equal f of b minus gamma, which will be greater than 0 if we assume by way of contradiction. that f of b is greater than gamma. Okay, so I'm doing this, and that's creating basically a strip up here that goes, it takes f of b, and my epsilon neighborhood of f of b is gonna go up and down by exactly that amount. Centered on f of b. So by the assumption, so since f is continuous at b, since f is continuous at b, now I'm gonna need a little more room, let me come over here. Since f is continuous at b, there will exist a delta greater than 0. Such that if, so I'm using the definition of continuity, that would be that if absolute x minus b is less than delta, then absolute of f of x minus f of b is less than epsilon. Okay, I should point out that we can kind of, undo the absolute value bars here, because in this case, the x values are never going to be bigger than b. Everything's happening between a and b. So in this case here, this is just going to be b minus x. I think it's, without rewriting the whole thing, I'll just replace it with absolute value bars. And similarly over here, remember that f of b, because of this increasing, f of b is greater than everything else in the set. So this becomes f of b minus f of x less than epsilon. Okay, so we know that. Okay. So if b minus x is less than delta, and by the way, our delta might be some neighborhood here, here's delta. Right, anywhere to the right of this point right here, you'll notice that f of x is within the strip, right? And what I could do is actually put in my epsilon now. So f of b minus f of x will be less than f of b minus gamma. And what you notice is the f of b's can be canceled from the inequality. I have f of b minus f of x compared with f of b minus gamma. So negative f of x less than negative of gamma. Okay. And I get rid of the minus signs if I'm willing to flip the signs. Okay, so in other words, this is just f of x greater than gamma. Ooh, so what that means is that if x is over here, somewhere within delta of b, what we're saying is f of x is greater than gamma. Actually, the picture does show that, right? Here's f of x, here's gamma, right? But what's the contradiction? Yeah, gamma was supposed to be an upper bound for all of the f of x's, and look what's happened. We have found a bunch of f of x values that are bigger than gamma. That would be for any x that satisfies this assumption here. We have now proven that f of x is bigger than gamma, and I'm just going to say contradicting gamma. It's a gamma, sorry. Contradicting gamma being an upper bound for the set of those f of x's where x is in the interval from a to b. And so that's the contradiction. So we're doing this forward direction by way of contradiction. Yeah. You guys feel okay about that? The one in the homework is super similar. Super similar, except you're working with infimums instead of supremums. Now this is only half the proof though. This is the forward direction. So if f is continuous at b, then f of b must equal the supremum of all of those f of x values, but we also need to prove the other direction. Yeah. Before I do that though, Make sure everybody's getting this. Are there any questions about any of this? Has everybody got it written down before I erase it? Because I know there's been a fair bit written down here. You can also take a picture.
To create our epsilon,
Uh-huh.
we just kind of.
You know, I pulled it out of the sky. You know how many times like we just sort of pull it out of, let epsilon equal 1. Let epsilon equal 1/2. We've done these kind of tricks a few times. You sort of have to just try something. And you know, you're thinking, for all epsilon greater than 0, I've got to be able to pick something greater than 0. Where in my proof am I going to see something that's definitively greater than 0? And that's where proceeding by way of contradiction here allows you to create that thing. I actually don't know how you would do it directly. I could go in there and think about it all night if I wanted, but yeah, it's much better suited to by way of contradiction because it allows you to create this positive number that you can play with, which I really like. Good question though, and you know, sometimes, yeah, it can be tricky to see, you know, how to create that epsilon out of the sky. It's something with time and practice and experience you get a little bit better at. You have to trust me that I'm not probably on a first pass through on 350 gonna ask you to create some epsilon that's really in left field, right? It should be something fairly obvious. Or in this case, something that's basically on the homework. For an exam setting, I have a different standard, right? I don't expect people to just dream these things up in 2 minutes of rushing through something. So let's try and prove the other direction. See if we can go backwards with this proof as well. So for the backwards direction, I'm going to assume that f of b is equal to the supremum of the set of all of these f of x's, where x is in the interval from a to b. And I claim that f is continuous at b. So I'm going to do that from the definition. The definition of f being continuous at b is that for all epsilon, there exists a delta such that then there's the condition. If the absolute value of x minus, in this case b, is less than delta, then the absolute value of f of x minus f of b should be less than epsilon. So blah, 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 saying it all out. Again, part A of this problem would probably be write down the definition of what it means for f to be continuous in b. All right, so anyway, so what's the first sentence I'm going to write now? Let epsilon greater than 0 be given. That is a rubber stamp statement. Just get that thing started. And our job is to come up with the delta. And this is normally where we would go over into some scratch work. So I might still use the picture. So remember that f of b, we're assuming here that f of b is the least upper bound. So if I take anything smaller than f of b, it won't be an upper bound anymore. I'll be able to leverage that. Is there a way to make something that would be smaller than f of b, even with what's on the board so far? How could I do it? Just with what's right here. This is all I got so far.
F of b minus epsilon.
If I subtract epsilon from f of b, I'll have something that's smaller than f of b. But f of b was supposed to be the least upper bound for the set. So f of b minus epsilon won't be an upper bound at all. Let's look at that, okay? So then f of b minus epsilon is not an upper bound for the set of these f of x's where x is in this interval from a to b. Oh, well, so that means that there's some f of x value that's bigger than f of b minus epsilon. Okay. So there exists an x naught in that interval from a to b such that f of x naught is actually greater than f of b minus epsilon. So by the way, this is, now I'm gonna edit my picture here. Here's my epsilon neighborhood around f of b. Up and down. And here's f of b minus epsilon, that's this blue line right here. And somewhere along the line, there exists an x naught. Maybe it's right here. There's an x naught such that f of x naught is greater than the bottom line, the lower blue line, the f of b minus epsilon. Right? So my f of x naught is already right here, guys, is already in this strip. Right? And if it's already in the strip, then everything to the right of it will also still be in that strip, because to the right of it, the function only goes uphill. But it never goes higher than f of b, right? Because f of b is my supremum. So I'm not gonna ever get higher than that. Oh, well, it looks to me like I can make a neighborhood that starts at x naught and goes to the end of the interval. And that's a delta neighborhood that I'm gonna make, that I need to make to prove that f is continuous at b. So let's see if we can do that. Let's let delta equal b minus x naught, and that will be greater than 0. I don't need to really put absolute value bars on that. And I think that should work. That should do it, right? In other words, delta is exactly this distance right here, from this dotted line over to the end of the interval. That's going to be my delta. Okay, and if we write down that positive value, all we have left to do is check that it works. Okay, so let's check that this delta works. Let's assume that the absolute value of x minus b is less than delta. Now, the absolute value of x minus b, as we know already, that's just b minus x, because the b is larger than x. And the delta was just b minus x naught. So I'll just go ahead and put that in there. And so I can cancel the b's, and that gives me negative x is less than negative x naught. And then I can take out the minus signs by flipping the inequality around. So that would mean that x would be greater than x naught. And guys, if x is greater than x naught, if I'm to the right of x naught, then f of x. Right, so now, if x is greater than x naught, then f of x is greater than or equal to f of x naught. That's the definition of increasing. The function is increasing. So if x is greater than x naught, then f of x would be greater than or equal to f of x naught. What am I trying to prove again? I'm trying to prove that the absolute value of f of x minus f of b, I want that to be less than epsilon. You know, so I'm gonna tell you guys right at this very second, I don't see how to do it. But what I mean by that is that I just haven't thought about it yet. I know it's going to work. This has to be the answer. So just calm down. Okay, if this happens to you, like, I'm just gonna take what I'm given and I'm gonna trust that this should end up being less than epsilon. First thing I can do is remove these absolute value bars, because I can switch the order. I can write it as f of b minus f of x. But if I subtract f of x, I'm actually subtracting more than if I had subtracted f of x naught. So I can replace what I've subtracted by, I'm going to go ahead and subtract less than I was subtracting before. You with me? And what can you tell me about f of b minus f of x naught? So look anywhere on the board where you see f of b and f of x naught together. This is right here, yeah? So look at that. If I rearrange that, I get exactly what I want. I get my less than epsilon at the end of it. So f of v minus f of x naught is definitely less than epsilon. That's the end of the proof. That's the end of the proof. Whew. Oh, this is a nice problem. This is one you shouldn't feel like, don't feel bad, like, oh, I don't know, I couldn't do that by myself. What I really want is that you look at what's in blue now and you can follow it, right? I think that's really the key. And can you follow it well enough to now go to the homework problem, if you haven't done it yet, and torque this thing around to work on the other end where we have f of a being the infimum of that same set. It's almost the same exact proof, but everything, the inequalities get turned around. I think you have less minus signs actually, but you have to flip around on it. So that might actually make it a little bit cleaner. Okay, questions on that? That's that one. I want to do one more and then I'll probably, it's 9 o'clock, but I'm gonna do one more anyway. If you need to go, of course, it's totally fine. I'll continue with more of these on Wednesday, but I'm gonna do one more for now. And then we'll do some more examples on Wednesday. I like all these problems actually. Okay, so where's the one I think I'm gonna do? Actually, it's this one. Okay, so number 8. One last problem for this review. Let's suppose, go back to sequences again. I keep going back and forth, right? Let's suppose that the sequence AN and another sequence BN, let's suppose that they are both Cauchy. So I haven't done anything with Cauchy sequences, so I think I'm gonna do one here. And then I'm gonna make yet another sequence, which I'm gonna define as C sub n to be just the absolute value of AN minus BN. Intuitively, if a sequence is Cauchy, it just means that all of its terms are getting very close to each other. We may not know what the limit of it is. We do know that Cauchy sequences converge. If we're thinking about it in R, we're not looking at Q or some restricted domain. If we're looking in R, then a Cauchy sequence converges, and so does this one. So these are two sequences. Each of them individually has terms that are getting relatively close to one another beyond some n naught point that we can define. And what I'm going to do is make this new sequence where I'm actually, now here I'm comparing the two to each other. So these values could be very large. Like maybe the A sub n's are all sort of hovering around 0 and the B sub n's are all hovering around 1,000,000. Okay, so this one's going to converge to 0, this one's going to converge to 1,000,000. So then these terms are going to be closer to 1,000,000, right? But what we're going to do here is we're going to prove that that sequence is also Cauchy. So if you subtract, in other words, if you subtract two Cauchy sequences, you essentially you get another Cauchy sequence. Okay. It is worth noting that all of the C sub n's are positive because we're taking absolute value bars here. We'll see where that comes in the proof. Let me just remind you of the definition here. So Cn is Cauchy. The definition just is here. By definition, so again, part A of this question would probably be to give me the definition of a Cauchy sequence, and then this would be for all epsilon greater than 0, there exists an n naught in the natural numbers, such that if n is greater than n naught, then m and n. Let me not mess up my own question. If m and n are greater than n naught, then absolute Cn minus Cm is less than epsilon. Yeah, so that's what we would expect here. Okay. So that would probably be the first thing I'd ask you. This was on the quiz actually. Most people did a good job, but just make sure you're really writing it out very clearly. Some people were like omitting words. Like I saw stuff like this. And they'd have such that mn greater than n naught, comma, cn minus cm less than epsilon. If I tried to read that out as a statement, I would trip over it, right? So I know this seems really super picky. But if there's ever a class where being picky is actually pays off big time for you, it would be this class. It really is important to write everything down precisely. So don't just be lazy with this. Don't just get kind of a rough idea what the definition. If you start leaving words out, I'm gonna start taking off points. Okay, so really have to get it very, very precise. Okay, so to prove that anything is Cauchy, and we don't have a lot of other theorems, by the way, about Cauchy sequences. So it's pretty much gonna be the definition, right? So we're gonna get into this here. The proof of something like this is just gonna start off with our usual rubber stamp. Let epsilon greater than 0 be given. And our job is ultimately going to be to come up with an n naught. And I'm wondering if anybody would like to propose how to maybe sort of launch this this proof from here.
We know that AN and BN have some in not, so to speak, that we can call N1 or.
I mean, we have an N1 here, we have an N2 here, these are already Cauchy, right? So we can use this definition with that, right? So let's absolutely do that. So I'll just say since AN and BN are Cauchy already, there exists an N1 in the natural numbers such that if M and N are greater than N1, then absolute AN minus AM, that's already less than epsilon. And in addition to that, there also exists an N2 in the natural numbers such that if M and N are greater than N2, this is something we've seen a lot, right? Where we have multiple N's that we have to sort of work with at the same time. Then absolute Bn minus Bm is also less than epsilon. Okay, and then what am I going to do? Does anybody feel confident to sort of write down a potential n naught here? The max of the two. Now, we've seen a few examples where that wasn't quite right. You might remember this, when I made the sequence where you alternated like x1, y1, x2, y2, x3, y3, and we had to actually choose n naught to be double of the max of the n1 and the n2. So I'm not gonna say you can just totally go on autopilot and just assume that the max of the two n's will always be the right answer, but it certainly is not gonna be a mid. And it is a reasonable thing to try to let n naught be the max of those individual n's. Let's just do that here. So n naught is going to be the max of n1 and n2. And then all I have left to do then, guys, is to verify that it works. So what I'm gonna do is I'm gonna let m and n be greater than this n naught. And because they're greater than n naught, it means that they're actually greater than both n1 and n2, right? So m and n are greater than n1, and m and n are greater than n2. Those are commas. So the m and the n, they're greater than both of them, which means, well, if m and n are greater than both of them, then that means both of these things are true. So thus, absolute AN minus AM is less than epsilon, and absolute BN minus BM is also less than epsilon. And at some point, we have to start looking at the sequence we're actually working with. All right, I need to prove that the CNs are Cauchy. So I need to look at Cn minus Cm. This is ultimately the thing that needs to be less than epsilon. Now, if I take that thing and feed in what Cn is absolute AN minus BN. And then CM would be absolute AM minus BM. So we get something that looks kind of like this, It's a little bit messy. Absolute value of all of that. Now that thing that we just wrote down probably reminds you, I mean, we can kind of write it a little more simplistically. It's an absolute value of the difference of two absolute values. Do we know anything about this?
Reverse triangle inequality?
There's some kind of a, modified triangle inequality for that, which would tell us that this is less than or equal to what?
Exponential.
Just
Or
absolute, just, so the difference between two numbers, right? Can only go down if you take their absolute values. So if you take two numbers and you see how far apart they are, and then you change it and you hit each of them with absolute value, now how far apart they are could only go down. Okay, so I'm gonna use that right here, guys. I'm gonna use this to replace this with absolute of, so I'm getting rid of the absolute value bar, so AN minus BN with parentheses this time. Minus, and then we have the parentheses AM minus BM. Okay. Now, anybody got a knee-jerk reaction, what you want me to do with that? Yeah, let's do a little basic algebra in here, let's get all the A's together and get all the B's together. And why am I gonna do that, just so I can be clear? It's because I know something about how far apart the A's are. And I know something about how far apart the B's are. When they're all mixed together, I don't really know a whole lot. So let's get them grouped up a little bit better. So I'm gonna write this as absolute of the quantity AN minus AM. Right, and then I'm gonna go ahead, if you guys don't mind, to put a plus here. I can do that because I've got a double negative on the BM, so I'm gonna write it as BM minus BN. So I'm just rearranging the terms, it's literally all I'm doing. I'm not even using this is literally an equal sign, it's not even a less than, it's the exact same thing. And what are you gonna have me do with that now, though?
Triangle inequality?
Now I'm gonna use the regular triangle inequality. You didn't think we were gonna get through 2 hours of Math 350 without seeing the triangle inequality show up at some point. And here it is, this is less than or equal to absolute AN minus AM plus absolute BM minus BN. So that's the regular triangle. So both the modified version and the regular version are both showing up in the middle of this proof. It's kind of interesting. And, oh, this one's less than epsilon, and this one's less than epsilon, but remember, I ultimately want this to be, according to my definition, less than epsilon. So, do I need to do anything?
Change to epsilon over 2.
Yeah, I knew 10 minutes ago that the epsilons here weren't really gonna work, but I don't like to assume that, like, I mean, if you don't see it coming, of course, you might just put epsilons here. And actually, if you did that and then over here you ended up with 2 epsilon, there'll be plenty of mathematicians who will tell you, oh, that's fine. As long as it's less than something that's indexed by epsilon, it's okay. But I kind of like it to fit a puzzle perfectly, and this is supposed to end up less than epsilon. So what we're ultimately gonna want here, guys, is epsilon over 2 plus epsilon over 2. This is gonna be an equal sign here at the very end of that. So it'll be less than epsilon over 2 plus epsilon over 2. But that does mean I need to go back. So now we just go back and we edit what we had before. If you didn't edit it and you left it the way it was, I'd give you 90% of the points for sure. It would be totally the right idea. So I gotta put epsilon over 2 here, epsilon over 2 here, because remember, we're assuming that these sequences are Cauchy, which means that we get to pick any epsilon that we want, including half of the given epsilon that we started with. So we can change this to anything that we want right here. Did I get it fixed in all the right places? Hopefully, I think so. Yeah, I think so. So that all shakes out then, and that works out nicely. So this is, I a nice problem involving Cauchy sequences. You don't ever know what these things are converging to. That never shows up in the proof. But it is a good reminder about the definition. Nice use of the triangle inequality, and we've seen this a few times where we've had to work with either two sequences or two functions, and we were adding them or subtracting them or something, right? And trying to say something about the combined sequence. So when you see something get presented over and over again multiple times, that's probably something you want to pay attention to. This idea of, this epsilon over 2 trick, and then using the triangle inequality, that's been, come up when we proved the limit theorems for sequences, it showed up. When we did the same thing for functions, it showed up again, and now here it's showing up for Cauchy sequences as well. So it's actually not that unusual. Okay. Let me just see here. Yeah, I've got some more practice. Like I said, I've done half of these problems. I think what I'll do is, and I think I've done a selection of them here. The ones I'm gonna do on the next review session will just be more hitting you with the same things again, with just, slight tweaks to what we've done. And so I think, if you can't make it on Wednesday, it should be okay. I didn't do a monotone convergence theorem based on the recurrence definition, which was on the quiz. By the way, I have your quizzes here, so I can give you your quizzes before I go. But I'll practice that on Wednesday as well. Maybe by then I'll have a better idea what I'm actually going to do for the exam. But I think this is pretty good, starting point. I probably would recommend, you're going to finish the homework by tomorrow. You might try that sample exam before the review session. The review isn't until, I guess you could wait, but then you're gonna. My only thing about waiting too long on the sample test is then if there are issues, like, oh my goodness, I need to go talk to Dr. Annan, or I need to do a bunch more practice, then you just don't have a lot of time, and it's a little frustrating. So I wouldn't wait too late to try the sample test. Having come to this review should be this together with maybe going through the review packet first. I think you should be ready to take on the sample test. I am going to head over to my office hours, and for those of you in Zoom, I'm going to end this review and then go over to my office hours Zoom room. So if you have questions, you want to talk to me tonight, I'm going to hang out pretty much till midnight tonight. So feel free to hang around if you're still having energy. If not, I know I'm a night owl, so I will be around again tomorrow, and we can certainly answer questions tomorrow about the homework as well, if you're still working on that. So, okay. Anybody out there in Zoom land have any questions? Oh, no, I don't think so. Okay. If not, I think I'm going to go ahead and call it a night. Thanks, guys. Thank you. Was this helpful?